Okay, so yeah, thanks to the organizers for organizing this really nice event. So what I'll talk about is a slightly different version of what Santosh just talked about. So this work is, so he's talked about a blast, which is like you have a 1D chain of particles, and you suddenly put a lot of energy at the center and you look at what happens, right? So here what we look at is like you have again a 1D system, and instead of putting energy at the center, you put energy at one edge. Okay, so, and then see what happens. So I'll describe in detail. And so this work is done with two really fantastic colleagues, Shubhadeep Chakraborty, and who was a postdoc here, and Paul Kropitsky in Boston. So let me just explain what is the basic question. So basically, there's a very nice book called Kinetic View of Statistical Physics by Kropitsky, Redner, and Benheim. And the cover of this book has this picture of a splash. Okay, so splash we all know, like if you have water and you drop something, there's a splash, right? So that's exactly the question. And so what you see here is like, okay, so you can imagine like there's a billiard table, infinite billiard table, and half of it is filled with balls which are at rest. Okay, and then at one end you strike it with a stick, and then ask what happens. So you just strike one ball, and then it goes and hits some other balls and some other balls and so on. And this is a picture that you find after some time, where the red colored balls are the balls which are moving. The rest of it is all static, right? And you can see that there are some particles which have got reflected from the system, and maybe they're moving out of the ball. So there's no gravity, nothing. It's just elastic collisions, and that's all. Okay. The blue balls are all at rest, but slowly you can imagine there's a front you can see, and it's maybe traveling into the system. And so we want to understand this. So this is the splash. Okay. So what's interesting about this system is that, like just now what Santosh was talking about is like you have everywhere cold gas, and then you want to study how this thing evolves, right? But this is a one-sided thing. And yeah, what's most interesting is that there's a regime where it's very dense system, where you can apply hydrodynamics. But then there's this particles which are going out, the splash particles, which you can't expect to use hydrodynamics, right? So that's why it's a very interesting problem. How do you understand a system where you can't completely use hydrodynamics? Maybe part of it is described by hydrodynamics. Okay, so I just saw that there are some very nice experiments people do on this kind of splash problems. Like you just take some sand and you drop a steel ball, okay, and so the ball goes and hits. So it's the sand is like small spherical particles, and you hit it with this huge steel ball. And then you look at the image of the sand, very fast images, so very short time images. And you initially, at some time, you find something like this. Then after slightly later time, you find that there's a long jet like this. Okay, if you blow it up, you find something like this. So this is quite interesting. And there's a lot of, experiments, similar experiments. Okay, so this is of course very complicated system. We want to think of the simplest example where a similar thing happens. Okay, so this is again the problem that Santosh just now talked about. Set of point particles. I've drawn balls, but it's really point particles on the real line. And we take them to be have masses small m, small m, and capital M, and so on. They're initially randomly distributed on the half line. And from one edge, I just start. So every particle is at rest, and then this particle moves with unit velocity, let's say. Okay, and you ask what happens. Okay. So this problem has been studied for if you have just n particles, not. So I'm studying the infinite system. People have studied the case where you just take n particles and ask like how does this system evolve? Okay, so these are like billiard problems studied by mathematicians. And one of the questions you can ask is like how many collisions are there, starting from some random initial conditions. And there are very interesting results. Okay. So we study the case where this is an infinite line, and you hit this guy and then ask what happens. Okay. So we'll study two, I mean, you can see that there can be two arrangements. You start with a small mass or you start with a capital mass, and this makes actually some difference. So these particles are labeled 0, 1, 2, and so on. And this is the initial condition. And the dynamics is very simple. They just move at constant speed. When they collide, there's elastic collision, which conserves energy and momentum. Okay, so now if I ask you, like, what do you think will this after some time, what do we think this first particle will do? Okay, so if you think a little while this two guys goes and collides with this guy, so then it will get reflected and start moving this way, and this guy goes and hits this guy, and this starts moving. So after hitting, then maybe this will the velocity of this guy goes down, and but then this can come back and hit it and so on, right? So it's not clear what's the long time situation going to be. Okay. So let me just tell you what happens. So after some time, you find that this guy just moves to the negative side with a constant velocity. Okay, and then maybe it suffers one collision or two collisions, and after that it never suffers any other more collision. It just keeps going to the left. The second particle, similarly, it suffers a finite number of collisions and then keeps moving left. Okay, so that's what the particles at the left end do. The particles inside are doing something more like they are a bit different. So let me just show you what is the time evolution of this system. Okay, so like if I just draw space-time trajectories, what does it look like? So this is what it looks like. So this is the leftmost particle. So this is space and this is time. So the leftmost particle out here, maybe it just suffered one collision and then just goes with a constant velocity. The second particle, maybe it suffered a few collisions and then moves with a constant velocity, and the third particle and so on. And on the right side, so x greater than 0, you find something interesting that there are here, of course, particles are suffering lots of collisions. And you see that this front here, this is the rightmost excited particle, and it follows, it evolves sub-ballistically. Okay, not ballistically, but slower than time. So, okay. And this is a zoomed up version of this thing. If I just look at like up to time 60, this is what it looks. Okay, so you can see it's some sense you can already see self-similarity. So this is what Santosh talked about, where you have particles on both sides, and so it evolves symmetrically. Right? But we want to understand this. So here you can see that you can describe the full system by hydrodynamics because it's a dense system. But here you can see that the particles out here are very rare, while here you have a dense gas. Okay, so that's the idea. X greater than 0, it's a hydrodynamic region. X less than 0, it's non-hydrodynamic. And so how do we understand this? What we find is that this front, the most excited particle on the right-hand side, it evolves like t to the power 0.55. And this is a bit different from the blast problem, where we saw that it goes as t to the power 2/3, right? 0.66, and this is 0.55. So it's a bit slower. So let's first understand how does this front evolves. Why? How does it evolve? Okay. So in the blast case, again, let me just remind you, this position of the front can be obtained from a very simple dimensional argument. So from dimension, we just expect that this front position should depend on the energy of the explosion, the density of the gas, and time. Okay, so then you put in something like this, and you immediately, just from dimension analysis, you get a formula like this, and so you get this t to the power 2/3, right? Now in the splash case, again, you can ask, like, why can't you use the same argument? And here what happens is that, like I said, this right hand part and left part are different. So we can kind of apply this argument to the right hand side, but then the energy is not really constant. Okay, because the splash particles are taking away energy from the system. So what we have to assume is that this energy actually decays with time, and so you get r goes as t to the power 2 minus beta by 3. And so okay, so now of course the question is, how do you determine beta? And what we'll see is that it reduces to the solution of a nonlinear sort of eigenvalue equation. Okay, so I already argued that the front of this blast evolves in this way, T2 or delta, where this, and then you can do some heuristic calculations to compute a lot of other things, like what is the total number of collisions in this gas, and you can find that goes as T2 or T delta. You can ask what is the total momentum carried by the this splatter. Okay, splatter is the splash particles, right, which are moving to the left.
Abhishek, you have 5 minutes.
5 minutes, okay. And then you find this thing, okay. And this, you can compare this with simulations and everything works. And the only unknown constant out here is this exponent beta, which is the energy decay. Okay, so we want to find this. Okay, so again, we'll use hydrodynamics to understand this. So the bulk of the system is described by these hydrodynamic equations, the Euler equations. And like Santosh said, that we expect somehow, and just like you see that it's true that at long time somehow you get scaling solutions, and the scaling variable is this x by r of t, and then you define this the scaling functions g, v, and z. Okay, so so now you plug this back into these equations, and you get some nonlinear ODEs. And now we again have to use some boundary conditions to solve these ODEs. So for the blast problem, we had this, so if you have a shock front, you can use some thing called Rankine-Hugenoid relations to find how the discontinuity at the shock front happens. Okay. So this leads to some boundary conditions at the shock front. But on the left end, we have a different situation where you have a non-hydrodynamic regime. And there we can argue that the boundary condition should look something like this. Okay, now you can solve these equations with this. And here we have this unknown parameter delta, which depends on this unknown parameter exponent beta, right? So it's like solving these ODs with some boundary conditions, and which you have to solve it self-consistently so that you get, and this fixes delta, okay? So this is the nonlinear eigenvalue problem, and we numerically solve this to find this exponent beta. And okay, so I mean, we do simulations, and this solution matches extremely well, and we see this scaling and everything works perfectly. Okay. So I just so then this is the bulk regime of the gas, which is described by hydrodynamics, and then you can ask what happens to the splatter particles. So the splatter particles, like I said, after a few collisions, the leftmost particles acquire a certain velocity, and then it continues. And then the next particle also, after a few collisions, it goes with some velocity and so on. And so every particle, after some time, its kind of velocity is frozen, and it just moves to the left with some velocity. Okay. So we have a few exact results for this side, for the eventual velocity with which a particle goes, and what is the number of collisions before that a particle faces before it goes, before its velocity freezes. So for this, we have some exact results. And then we have two conjectures which look really, I mean, obvious, but it's very hard to prove, and at least we have not been able to prove, which is that this statement that the collision velocities eventually freeze. And so I had two arrangements, like small m, capital M, small m, capital M, and capital M, small m. For the first arrangement, what we find is that the leftmost particle has only one collision. Okay, after that, it just goes with a constant velocity. So for whatever the initial conditions you choose, it goes has exactly one collision. And this is again something we observe, and it seems kind of obvious, but it's very hard to prove. Okay, so we haven't proved this. So I'll just end by saying that these are some open problems. There are these two conjectures we have. I mean, it seems very obvious, but it's very hard to prove. And then, of course, the analytic solution of the Euler equation, similar to what this TVNS solution that Santosh talked about. I mean, can one actually solve these equations analytically and get it? So this is the reference, which right now it's there in the archives. Thanks.
We have time for a couple of questions.
Am I audible? Okay. Yeah, thank you for the very nice talk. I just had a question regarding the same setup where you have these masses, but say instead of the masses, you were to replace them by, say, charges, for example, positive charges, which basically have a long range force. Do you expect qualitative differences in the behavior, or would it be similar?
Uh, yeah, if it's long ranges forces, of course, it's very like if it's short range forces, I would expect it's more or less the same.
I see.
If it's long range forces, it could be very different, right? Yeah. Yeah.
Okay.
I mean, definitely it would be quite different.
I see. Okay.
We could take another question.
Yeah. I have a somewhat vague question.
Yeah.
Yeah. So, I mean, is there any expectation as to whether beta should be rational or irrational or maybe transcendental?
Yeah, no. So yeah, initially actually we had a guess that it's 1/8, and but then it's what we found numerically. I mean, is this number, and we tried actually trying to guess various things. But okay, I mean, right now we have no idea it's rational, irrational, or transcendental, because it's coming from the solution of these equations, and it's probably not rational, definitely, because. Okay, I mean, we tried sort of making rational approximations, and it doesn't look like there's a small number. And so, yeah.
Okay. Thank you.
Let's thank Abhishek for the wonderful talk.